Hello, friends. Can you imagine this Earth? The same Earth on which we humans were born, the home of countless living beings, was once 4 billion years ago a boiling ball of lava, a lifeless, scorching sphere with no trace of life. Naturally, the question arises: how did this fiery planet transform into the Earth we live on today? Where did all the water come from? How did our moon form? The answers to all of these questions lie in the birth of our sun and the solar system. Let's understand this fascinating process in depth. The birth of our solar system about 4.6 billion years ago, our solar system didn't even exist. There was only darkness, a deep calm and empty space. Floating in that space was a giant cloud of dust and gas, known as the solar nebula. It mainly consisted of hydrogen and helium. For billions of years, this cloud quietly floated in space until one day, a supernova exploded near it. Not the Big Bang, but a nearby dying star exploded and sent shock waves into the solar nebula, triggering gravitational instability. These shock waves caused regions of gas and dust in the cloud to collapse inward. Over time, the whole cloud began to shrink and spin into a flat rotating disk, known as the protoplanetary disk. This explains why our solar system is flat. All planets revolve almost in the same plane. At the center of this spinning disk, pressure and temperature increased. Eventually, a protostar was born, the early version of a star. The matter in the nebula was drawn inward by gravity, getting hotter and denser, until nuclear fusion began. Hydrogen atoms fused to form helium at around 15 million C, releasing energy. This process gave birth to our sun, and it still powers the sun today. Formation of planets. While 99.8% of the solar system's mass went into forming the sun, the remaining 0.2% formed the planets, moons, comets, and asteroids. Within the spinning disk, tiny dust particles collided and stuck together due to static and chemical forces. Over millions of years, these grew into planetesimals, then protoplanets through a process called accretion. This concept was proposed in 1969 by Soviet astronomer Viktor Safronov, and it's now widely accepted. Evidence of this process can also be found in meteorites, especially small rock grains called chandrules, which are older than planets themselves. Some contain radioactive elements like uranium and hafnium, helping scientists date them. Violent collisions and Earth's birth. In the early solar system, protoplanets frequently collided, releasing immense energy. These impacts melted rocks and created seas of lava. Over time, the growing bodies became more spherical due to gravity. One of these collisions led to the formation of Earth. During the Hadean, Earth was bombarded by objects as large as 100 to 200 kilometers, creating extreme heat and a magma ocean. But surprisingly, this destructive era led to the arrival of water. Some comets and asteroids that struck Earth contained ice crystals, remnants from the solar nebula. Over time, the water vapor condensed and fell as rain, eventually forming oceans. Earth's differentiation into layers. As the Earth cooled, heavier elements like iron and nickel sank to the center due to gravity, forming the core, while lighter elements like oxygen, silicon, and aluminum rose to form the mantle and crust. This separation is called differentiation. Today, Earth consists of 3 main layers: crust, mantle, core, but geologists further divide Earth into 5 layers based on physical properties: lithosphere, asthenosphere, mesosphere, outer core, inner core. The core is incredibly hot, but the immense pressure keeps the iron and nickel solid. One major source of heat is radioactive decay from elements like uranium, thorium, and potassium in the mantle. Moon formation, the giant impact hypothesis. Where did the moon come from? There were many theories capture co-formation, fission, but none fully explained it. The most accepted theory today is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized protoplanet named Theia collided with the early Earth. Their cores merged, but the debris ejected from the impact formed the moon. Evidence from Apollo missions shows moon rocks are chemically similar to Earth's, especially in oxygen isotopes. This supports the idea that the moon originated from Earth's outer layers after the collision. Interestingly, this impact also tilted Earth's axis to 23.5, giving rise to seasons and created a stable magnetic field that protects Earth from harmful solar radiation. Oceans and life. During the Archean Eon, Earth cooled enough for rain to fall, creating oceans. These oceans absorbed CO and heat, stabilizing Earth's temperature and making it hospitable for life. Volcanic eruptions released gases like water vapor, CO, methane, and ammonia. A harsh mix, but essential for early life chemistry. Over millions of years, various rocks formed. Igneous rocks, metamorphic rocks, sedimentary rocks. Sedimentary rocks formed through weathering, as sunlight, wind, and water broke down existing rocks. In conclusion, Earth's journey from a fiery ball to a life-supporting planet was shaped by cosmic accidents, natural laws, and immense timescales. The layers, oceans, moon, atmosphere, and seasons all emerged from this long and dramatic history. A story written in the rocks beneath our feet and the stars above us.